So now we have the definition of an eigenvalue. A number lambda is an eigenvalue of a matrix A if the difference between A and lambda times the identity is a singular matrix. The question now is, well, what's the significance of the singularity of A minus lambda times the identity? To answer this question, we need to build the concept of an eigenspace. So the eigenspace of a matrix A associated to an eigenvalue lambda is notationally referred to as this maybe cursive E sub A of lambda. And this is defined as the null space of A minus lambda times the identity matrix. So the eigenspace associated to an eigenvalue is the null space of A minus lambda times the identity. And the eigenvectors that live in this null space, the eigenspace, are called the eigenvectors of a matrix associated to the eigenvalue. Now, one important thing to point out is that we're defining the eigenspace as the null space of a matrix. And the one thing we know about this matrix, A minus lambda times the identity, is that when lambda is an eigenvalue, that means A minus lambda times the identity is singular, which means its nullity is at least equal to 1, which means that the dimension of this null space is at least equal to 1. So the first thing we can say about eigenspaces is that their dimension is at minimum equal to 1, because by definition of the eigenvalue, A minus lambda times the identity is a singular matrix. So eigenvectors are the vectors that live in an eigenspace. But a natural question to ask is, well, what is an eigenvector exactly? Why do I care about the vectors that live in the null space of A minus lambda times the identity? So the first thing to point out is that, well, by definition, a vector lives in the null space of A minus lambda times the identity means that A minus lambda times the identity multiplied by that vector equals the zero vector. So the eigenvectors living in an eigenspace are exactly the vectors V that satisfy the equation A minus lambda times the identity, all multiplied by V equals the zero vector. And now let's point out that if we distribute V here, we end up with A times V minus lambda times the identity times V, which is really just lambda times V equals the zero vector, which is the same thing as saying that A times V equals lambda times V. So this calculation is telling us that the vectors in the eigenspace, or the eigenvectors of a matrix, are exactly the solutions to what we previously called the eigenvalue problem associated to that matrix. So the punchline is that eigenvectors are vectors that solve the equation A times V equals lambda times V, where lambda is an eigenvalue of the matrix. Now, this is geometrically relevant, as we've pointed out before, because this is the same thing as saying that the output of multiplying A by the eigenvector is parallel to the input, or that vector. So let's state this as a theorem. V is an eigenvector of A associated to lambda if and only if A times V equals lambda times V. So let's look a little closer at the geometry of this situation. So again, when we're dealing with a square matrix, we can visualize the transformation where the input vectors live in the same space as the output vectors. So here we're looking at the 2 by 2 matrix whose columns are 1, -1, and 2, 4. Let's say we multiply this matrix by the first standard basis vector, 1, 0. The output of this process produces the vector 1, -1, which we're recording over here. Let's say we multiply this matrix A by the second standard basis vector, 0, 1. The output of that produces the vector 2, 4. So again, because this is a square matrix, we can superimpose these two images, and what do we get? we get E1 plotted with its output, A times E1, and we get E2 plotted with its output, A times E2. And one thing we can recognize visually here is that the output, A times E1, is certainly not parallel to the input, E1, and same goes for E2. The output, A times E2, is certainly not parallel to the vector E2. So this one image communicates the fact that E1 and E2 are not eigenvectors of this matrix. So let's change the input data a little bit. Instead of thinking about the input vectors E1 and E2, or 1, 0, and 0, 1, let's look at the vectors 1, 1, and -2, -1. So we have the same matrix here, but now the first vector we're going to multiply by is 1, 1. So 1, 1 is plotted here in blue. When we multiply A by 1, 1, what we're really doing is we're adding the two columns together. So we really produce the vector 3, 3. So that's our first output vector. Let's look and see what happens when we multiply A by the vector -2, -1. To multiply this matrix by -2, -1, we first scale the column 1, -1 by -2. So that gives -2, 2. And then we subtract the second column. That produces the vector -4, -2. So let's now superimpose these two images. So we started with the vector v, and when we multiplied by v, well, v was 1, 1, and A times v was 3, 3. So what we're noticing is that A times v is 3 times v. And geometrically what's happening is that we have our input vector v, and its output is 3 times the input. This is telling us that v belongs to the eigenspace of A associated to the eigenvalue 3. What about w? Well, w was the vector -2, -1, and when we multiplied by A, we produced the vector -4, -2. Well, -4, -2 is 2 times -2, -1. So what we're finding in our figure is that w is an eigenvector of our matrix, and the associated eigenvalue is lambda equals 2. So that's why we're writing here, w belongs to script e sub a of 2. So our picture for this example is different from the previous slide. On the previous slide, the input vectors were not parallel to the output vectors. In this example, the input vectors are parallel to the output vectors. Okay, so let's look at some other examples and see how eigenvectors fit into the conversation. So let's consider the projection matrix P onto the xy plane in 3 dimensions. This is a matrix that we studied earlier. Well, how does this exactly work? What we do is we take any vector in R3, and we to project onto the xy plane, we sort of smush that vector onto the xy plane. Mathematically, what that entails is dropping an orthogonal from the tip of the vector to the xy plane. And then wherever that orthogonal hits the xy plane, we can connect a vector from the origin to that location, and that gives us projection onto the xy plane. Now, of course, we could figure this matrix out by looking at what this does on coordinates. And we end up with the 3x3 matrix that's diagonal, where the first 2 diagonal entries are equal to 1, and the third diagonal entry is equal to 0. Now, the eigenvalues of this matrix are equal to 0 and 1. Now, we can see that from this particular matrix, because this is a triangular matrix after all, and the eigenvalues of a triangular matrix are just the diagonal entries. There's another way to think about this, though, and that's through the lens of eigenvectors. Let's think to ourselves, what happens in the equation p times v equals 0 times v? Well, p times v equals 0 times v is really the same thing as saying p times v equals the 0 vector. And if we wanted to find vectors v that satisfied this equation, we would be looking for vectors in 3 space that collapse to 0 after we project onto the xy plane. And those vectors turn out to be exactly the vectors that live in the z-axis. So in the figure representing projection onto the xy plane, the z-axis represents the eigenspace of this matrix associated to the eigenvalue lambda equals 0. We can also look at the equation p times v equals 1 times v, which is really the equation p times v equals v. Well, the v's here represent all of the vectors in 3 space that are not changed when we project onto the xy plane. And of course, those are the vectors that live in the xy plane, or the vectors that have 0z component. Well, all of those vectors live in the eigenspace of the matrix P, where the eigenvalue is equal to 1. So the eigenspaces can be explicitly described for this example. The eigenspace for this projection matrix, this A should say P, by the way, the eigenspace for this projection matrix for lambda equals 0 consists of all of the vectors in the z-axis, and the eigenspace for this projection matrix, again this A should be P here, associated to lambda equals 1 is equal to all of the vectors in the xy plane. This generalizes to this observation generalizes to a theorem about projection matrices in general. Let's say we're studying a projection matrix onto a vector space V. The eigenspaces of that projection matrix, well, they come in 2 flavors. The first eigenvalue of any projection matrix is equal to 0, and its eigenspace is the orthogonal complement of the vector space in question. And the second eigenspace of a projection matrix corresponds to lambda equals 1, and that eigenspace is equal to the vector space in question. So projection matrices always have 2 eigenvalues. The first one is lambda equals 0, and its associated eigenspace is the orthogonal complement of the vector space in question. And the second eigenvalue is lambda equals 1, and its eigenspace is equal to the vector space in question. This is compatible with the example we just did, where we were projecting onto the xy plane. To project onto the xy plane, well, we're dealing with a projection matrix, so its eigenvalues are 0 and 1. The eigenvalue lambda equals 0 has eigenspace equal to the orthogonal complement of the space in question. So here we are projecting onto the xy plane, and the orthogonal complement of the xy plane is the z-axis. The second eigenvalue is lambda equals 1, and its eigenspace is equal to the vector space that we're projecting onto. Again, here we're projecting onto the xy plane, so the eigenspace for lambda equals 1 is equal to the xy plane. Another important matrix is the rotation matrices in 2 dimensions. So this is a new fact for us. Counterclockwise rotation in 2 dimensions by an angle theta is given by this matrix R sub theta, where the columns are cosine theta, sine theta, followed by negative sine theta, cosine theta. So let's just, for example, say that we were rotating in 2 dimensions by a right angle, theta equals pi over 2. Well, when we plug in theta equals pi over 2 into this formula for rotation, we get a 2 by 2 matrix whose columns are 0, 1, and negative 1, 0. The idea is that whenever we multiply a vector in 2 dimensions by this matrix, the output vector is equal to the input vector, but we rotate by an angle of pi over 2 in the counterclockwise direction. So here we see just some vector in R2. After multiplying by the rotation matrix, what we're doing is we're rotating by an angle of pi over 2. And one thing to observe for this particular matrix is that the input vector v is never parallel to the output vector after multiplying by rotation by pi over 2. What this is telling us is that this rotation matrix does not have any real eigenvalues. So what we're going to find momentarily is that when working with eigenvalues, we cannot escape the world of complex numbers, but we sometimes do escape the world of real numbers.